Good evening, everyone. How are you doing tonight? I'm Xe Iaso, and tonight I'm going to talk about function calling, or how tool use works with large language models. I've seen a lot of people misconstrue this, especially with recent product launches, and I think that a more fundamental understanding of what's actually going on will help everyone here. Spoiler, the model isn't actually calling the functions. I'll get into it. Before we get started, though, I want to explain how I wrote this talk and why. I frequently get asked if I use AI and large language models to help me write my talks because I write a lot of them. It's kind of my job. Generally, I don't, and there's a good reason why. They're bad at it. They're really bad. As a bit of an experiment, I used an AI model to help me take a Slack rant and turn it into an outline that I turned into this talk, and let's see how it comes out in practice. Please let me know. I did have the AI write some parts of it, though, like, as technology continues to evolve, generative AI models are able to process and fabricate human-like language. But what makes these models tick? How can we use them productively in our scalable workflows? Let's dive in. Before we get started, though, I want to introduce myself. I'm Xe Iaso. I'm a technologist and a philosopher who's passionate about exploring the intersection of technology and human experience. As the senior techno-philosopher at Fly.io, I've had the privilege of working on cutting-edge projects that blur the lines between code and creativity. I have a decade of experience in this industry. I've seen the hype cycles come, and I understand that there's a lot of things changing, and amidst all this change, we don't know how any of this stuff works. In this talk, I'll be delving into the world of large language models. These models have revolutionized the way we interact with technology, and even though countless people have used them to generate essays, code snippets, or images, very few people understand how this nonsense actually works. Let's change that. I'm going to curse you with knowledge. So, many people have misconceptions about how this stuff works, and let's set the record straight. In this section, we're going to explore some common myths and misunderstandings and bust them so that you can help navigate the hype. So I can help you navigate the hype. So, many people assume that the large language model is magic. It's not magic. We can explain it kinda. That makes it science, well, computer science. But it's really just a lot of stuff going on, and it's really dumber than you think. All the model really has access to is the context you give it and anything it outputs. And okay, in terms of knowledge, let's be clear. We don't really understand how knowledge works, but we think that the closest analogy to what large language models have in terms of knowledge is rote memory, or like your times tables. The devil's in the details, and they do a lot of details in order to hide this. Another common misconception is that they're super intelligent, having all-seeing power or omniscience or whatever, and no. They're certainly impressive for being souped-up autocomplete, but they're no. A model's capabilities are limited by this task that it was intended for and the data that it's trained on. A model trained on medical text may be great at summarizing some medical records or something, but if you ask it to write a creative story, it's going to be very, very bad at the job. By understanding the limitations of your tools, you know how to use them better. And if you know what the limitations are, you can design your tools to avoid them. But let's be clear, another thing that's not helping here is the hype cycle. Oh my gosh, the hype cycle is creating products that seem like they're magic, able to do things. But the horrifying truth of the matter is that large language models can do anything, as long as that anything is generating text. That's it. Most of it is really just generating text in different flavors, like JSON. The systems around the model are what turn that text into real-world actions. And this predictive capability is kind of overstated because some people think that large language models see the future, and they don't. Humans are just really bad at repeating themselves. If your phone says, notice that you says, I love you a lot, and you type in I love and it predicts you, is your phone sapient? No, it's just seeing a pattern. Add that up with all of human language, and there's a lot of patterns that are the same. Some thorns have roses. So now that we've covered the concepts and misconceptions, let's double click and drag on the details. When we train large language models, we typically feed them a bunch of text, and they infer patterns from the text, and those patterns are what we call weights. There's two fancy terms for how this is done, but they're both different variants of the same thing. There's basically throwing Wikipedia at it and seeing what happens, and throwing chat logs at it and seeing what happens. They're supervised and unsupervised learning. Supervised learning is where you have an output that you want the model to get, and it will train, and if it gets closer to it, then you reward it, and if not, then you punish it. And unsupervised learning is when you throw Wikipedia at it. Both of these are essential because it allows the model to pick up language patterns in different ways. So if we're really throwing chat logs and Wikipedia into a blender, what makes this useful? There's a few factors at play here. Large language models are often trained on massive amounts of data harvested from various commercial and non-commercial sources. It's not inaccurate to say that things like GPT-4 are probably trained on the sum of all human knowledge. There is billions or trillions of tokens that they have to select between to train it on, and that scale adds up, and oh my goodness, there are so many complex relationships with data. And human language is complicated. We are actually in a unique position in which we can for real tell that art is less complicated than language, because the models for stable diffusion are like 600 million parameters, while the best models for human language are in the billions. That's like several orders of magnitude different. Realistically, if something's slightly wrong in art, you won't notice it. But if someone uses a instead of an, you'll notice it instantly. Human language is complicated, and the models have to be complicated to compensate. And all of the training methods that I mentioned, it all adds up to make it work. And large language models, even though the models themselves are complicated, the actual underlying architecture is really simple. It's just literally the same thing as autocomplete. Like on your phone right now, if you use an iPhone, you use the same model architecture as ChatGPT, asterisk. And as a result, training this requires significant computational resources, and that is a major bottleneck. At work, we've been trying to get new GPUs from NVIDIA. The procurement times are over a year long for 2-generation-old cards. And even then, the cards that we get, they could be more useful by having $5 worth of more video memory that they just don't put on the fucking cards. No, seriously, this is so frustrating. I don't even know how to begin to express this. And this lack of memory and the lack of throughput from NVIDIA means that training cost is expensive, the hardware is expensive, and it just takes longer. And we've seen an example of this recently with Google and data quality. The algorithm does not know satire. If you train the model on sarcastic instructions on using non-toxic glue to stick cheese to pizza, guess what the model's going to tell people to do? It does not have a theory of mind. It does not have a theory of what makes sense. All it knows is these words go together, so they must be right. And interpretability. Large language models are basically the classic example of a black box architecture. A black box architecture is something that you can put input in one end and you get an output on the other end, but you don't really know what happens in the middle. And that's because it's basically too many dimensions for humans to keep track of. It's like 20 layers of billions of different parameters getting massaged with tokens and weights, and no, you can't. Don't even try. And this, of course, has resulted in one of my favorite cottage industries to track. Paid PDFs on LinkedIn on how to best get ChatGPT to do your job. No, I'm serious. This is an actual thing. So, so that I can continue to crush your expectations of what these things are, here's what large language models are not. They're not super intelligent, they're not universal tools, and they're not a path to the machine god. Sorry, Rocco, you're safe this time. So, one of the words that I threw around there is tokens. Tokenization is how large language models get trained on words and how words are split up so that the machine can understand it. We understand text much differently than machines do. Let's take this quote by a classic philosopher of the ages into consideration. We're no strangers to love. You know the rules, and so do I. As humans, we break this down into units of speech like words, clauses, and phrases, and we know what's going on. This is not what an AI model sees. Here's what the OpenAI tokenizer says about this quote. Oh, wait, there. Double tap. These 59 characters break into 16 tokens. These tokens are a really fucked up Huffman tree of all of human knowledge. And this is why the models have difficulty with spelling and math, because all it knows are these separate tokens and nothing else. It doesn't know the letters in them unless it's trained on it, but then you have to train it on, all the possible spellings of everything, and that doesn't help because American, Canadian, British, Indian, and Kenyan English all have different spellings for everything, and it's a miracle spell checking even works. And oh, I'm sorry. I need to clarify a bit further. The model doesn't actually see the words. It sees numbers, and the numbers correlate to the different tokens in the training set without any context to what those words are. Anything the model learns about the words is merely just inferred from the training set. And the platforms that your models run on go great effort to hide this, yet charge you for the amount of tokens that you use. So realistically, let's say we have a model, we are able to give it input, we're able to get output. What goes next? The raw foundation models, not trained on chat stuff, are pretty good for things like summarization or text completion, but they're not really that useful. We need to have a layer on top of the tokenization to define packets and messages so that we can get something close to a human conversation. In the industry, we use many systems to do this, but because this is my talk, I'm going to talk about the thing that I'm most familiar with called ChatML. ChatML is an encoding system where a stream of tokens can be broken into messages based on the roles of the interlocutors, ooh, that's an SAT word, and uses magic tokens to mark the start and end of messages. So here's an example ChatML session between a user and an assistant with a system message. So there's 3 messages here. The first is a system message that tells the model who they are, what's about them. In this case, we're talking about one of my projects, Mimi, a helpful programming assistant. And the first question is the user asking why the sky is blue, and for some reason, this is the example response, even though the sky is blue because air is blue. But realistically, those magic IAM_start and IAM_end tokens are what break this stream of things into packets, and then we can turn those packets into JSON. Hint, the shift key is not the arrow key. And then you get something like this back from the platform, right? And then you can take that and you can put it into your chat UI thing, and everything's hunky-dory. And these abstractions allow the model to emit a stream of tokens that are parsed by the environment and then sent through to the client, so you have the facade of communication. Everything's wrapped up into the bubbles of the chat apps that I see at least 2 of you typing in right now. I'm not judging. Those magic tokens, the IAM_start and the IAM_end, are what the model is trained on when you throw chat logs at it. If the model ends its turn, the runtime stops generating new tokens, otherwise it'll get really weird really fast. This type of training is called instruction tuning. If you see -instruct models on Hugging Face, that's what it means. And with this level of abstraction, we have the ability to tell the user why the sky is blue or answer any other questions in the rote memory of the model. However, that's just telling people things that it's been trained on. That doesn't really make it useful in the real world. To make it useful in the real world, we add tools. At a high level, when you make a model choose between tools, you effectively have it classify the input to see which tool is the most applicable. For example, if the user asks about the weather in Cincinnati, you probably want to use a get temperature in city tool to get the answer, you know? The model would need to signal to the runtime that it needs to use a tool, and so that way the runtime can pick that up and do whatever it needs to, right? So let's say you have that list of tools on the slide before, and the user asks the question, what's the traffic situation like on the Bay Bridge? Given the list of tools, the model can tell that it might need to do a Google search. So for the sake of argument, let's say that you've trained your model to emit this magic tool call token with special JSON whenever it needs to use a tool. When the runtime sees this, it'll try to parse the JSON output and then execute the tool. And if it can't parse the JSON output, it'll just do it again. Yes, this is really how they do it in production. It horrifies me too. There's techniques to make the model output JSON by using grammar to weight all of the ungrammatical tokens in JSON to negative infinity, but that's an implementation detail and we can skip that for now. But let's just say that the model the perfectly spherical model is capable of generating perfect JSON in a vacuum whenever that tool call token is emitted. So the runtime does the Google search and oh no, it got something from the Onion. And the Bay Bridge is in chaos after a Tecaro brain plant patient gets out of their car to do a dance? Oh, I guess that's what's going to be put into the context window now. Oops. And then the model emits something like this. And this is how you give the model the facade of actually being able to do things when it's not being capable of being able to do it in the first place. It's just picking between the tools it has available, choosing to execute one, getting the results in the next iteration, and then generating some new text or even another tool call based on the results. And this is all well and good if you want to chain yourself to the chat interaction model. But why would you? If you don't have to chain yourself to something, why would you? When a model uses a tool, it generates JSON. JSON is the lingua franca of interoperability between things. This lets you turn a large language model into a compiler. And so, with that in mind, I think these are going to be the use cases of large language models after the hype cycle dies down. So you remember them better, I've made them all end in shun. So the first one is classification. Classification is when the model takes something and puts it into different buckets, like a positive tweet or a negative tweet, or user wants information about the traffic on the Bay Bridge, or user wants information about, I don't know, the weather in Cincinnati. This is the type of stuff that is used to build something like Siri. And then another thing that they will be used for is summarization, or given a bunch of words, give me a shorter version. This could be anything from complicated reports to get the key takeaways like you can on LinkedIn. You can look through financial reports to see what's changed since last time, or even convert Linux kernel commits to plain English, allegedly. And finally, fabrication is when the model just makes some stuff up that you happen to believe is correct. The main difference is between fabrication and hallucination is fabrication is stuff you agree with, while hallucination tells you to glue cheese to pizza and put your dog into a hot car. So these three basic things that large language model provides, when you combine them, you can do basically anything. You can get your model to provide users with the exact information you need it. You can have it generate a SQL query and then run it against a database. You can do basically anything you need. Imagine being able to ingest the entire specification for an obscure programming language, the documentation for the standard library, and the source code file you're looking at to be able to get something to start with towards a solution. This is where the real magic sets in, and it helps you avoid the terror of the empty canvas. And this all adds up to give the user the impression that the model is intelligent when it's really just a bunch of unintelligent components in a trench coat. It's not really smart, but everything around it is really good at making you think it is. Throughout this talk, we talked about large language models. We started from the beginning of what they are, what they aren't, how they're created, how they end up being useful, and hopefully I dispelled a lot of the hype-based misconceptions. But one more thing to consider, one of the biggest strengths and weaknesses to large language models is the fact that their output is inherently random. Let's consider a classic quote from IBM. A computer can never be held accountable. Therefore, a computer must never make a management decision. This quote was written in 1979. Time had only existed for 9 years. This was before Java. This was before Linux. This was before, like, the desktop computer. And does your app really benefit from unpredictable randomness? If not, like, I get the hype, but large language models really may not be for you. Oh, and you thought this talk was only theory. Think again. I've written a little program called Rant2Outline based on the way that I took a giant Slack rant and turned it into the outline that I used to make this talk. Don't believe me? See the demo for yourself. And yes, it's called Recipificator because originally it was going to be for turning YouTube cooking video subtitles into a recipe, but that ended up turning out very badly, at least 20% of the time. So I don't want to have you accidentally make magic crystals and, you know, hurt yourself. And if you want to clone this for yourself, it's on GitHub. The link is on the next slide and in the description. And with that, I've been Xe Iaso, and I hope you have fun. I hope you've had fun. I'll be wandering around with stickers in case you have any questions. Just look for this Technicolor Dreamcoat. You can probably see it from orbit. Have a good evening, y'all. Actually, does anyone have any questions? Okay, so the question was, you said large language models don't have a theory of mind. What do you mean by a theory of mind? I was told to avoid using the word soul, but I have run out of other words to use. So, like, you know, the spark of whatever that makes humans different from machines, like, I don't know what it is. But so you asked, like, given existing patterns, being able to infer new ones. I believe large language models can do that, but, like, we're probably getting deep into the philosophy zone, and I think none of us are at the 3-drink minimum for that kind of conversation. Like, I'm sorry to shut you down, but, like, I'm going to be very cautious here and say I really don't know because I just do not. Okay, the question was, one of the challenges with large language models is randomness. What do you think would be gained with deterministic sampling? I don't know. It depends on what the determinism is and how it was trained, because if it was trained on telling you to glue cheese to pizza, you know, something, something, Google AI suggestions, something. Is the problem, okay, so given this quote about a computer not being able to be held accountable, if the AI is made to be deterministic, is the problem of accountability solved? Okay, let's say for the sake of argument, this is probably a 3-drink philosophical statement. Sorry, but let's say for the sake of argument, somebody creates a device that uses an AI model to determine that another human should no longer be living, and that AI model was wrong. How do you put ChatGPT in prison? Who is responsible for that? Like, well, okay, so I guess the determinism versus non-determinism isn't the part that makes it accountable. I guess it's the accountability is like, if a person makes an error, like they can be held accountable and punished by society for it. Like, you know, being sent to prison or made to pay reparations to the family of the person that they harmed. But like, we can't put ChatGPT in prison, can we? Like, I don't know if that makes any sense. Do we just take like the A100 in question, sequester it out and throw it in a jail cell for the rest of its digital life? Like, yeah, I'm a sci-fi writer, and this like edge of how these two things intersect is something that I've been really thinking about a lot. And all of the AI hype has actually made it really hard for me to write sci-fi because I write satire, and I usually write this very thin line between funny and depressing, and the stuff that has been happening is so wild that I can't compete. Like, I have tried to compete, I just can't. Cool, thank you so much. Have a good evening, y'all. Where's the pen?